Hello, welcome to another session of statistics. This video will actually show you how to do chi-square. In the last video, we learned how to do chi-square, but we learned how to do chi-square using a method called goodness of fit test. Today, we're going to do chi-square, but we're going to look at how to do it using what we call the independence method, right? Or independent method. Now, I'm going to explain how it works, and then we're going to solve a question, and you're going to see how easy this is. The thing is that in the goodness of fit method that we learned, remember what we did was you were given an expected frequency. You now did your own survey or your research or your sampling, and you got your own distribution. And so the goal was to see if your distribution or your results was the same as what was expected or it was different. In independence method, we do it a little bit different, right? Here we want to see if there's a relationship between variables. So similar to probability. If you remember, in probability, we say an event is independent of another if the occurrence of one has no effect on the other, right? Remember, in probability, if, for example, you toss a coin, or let's use a die, right? If you throw a die and you get a 4, right? The first time you did it, right? That has no effect on the second time you throw that die, right? You could still get a 4 again, you could get a 5, you can get a 6. The 4 you got from the first trial just has no effect on the second one. And that's a scenario where it's independent. But on the other hand, remember, if you are doing conditional probability, it is dependent. So a good example of conditional probability is, it is raining. Will you go to work? Now, there is a chance that you may not go to work because it has rained. And that means that the rainfall has affected your next move. That is an example of a dependent event. So the first scenario was independent. The second one was dependent. Now, in chi-square that we're going to study today, using the independence method, we use contingency tables, right? But the key thing is that it shows the observed frequency for 2 variables, and the observed frequencies are arranged in terms of rows and columns, right? And the intersection between those rows and columns usually is called a cell. Now we're going to solve it together, and you're going to see how it works. I just want to give you the basic explanation, right, of how it works. So it's going to be arranged in terms of rows and columns, right? Now there's a slight difference between what we did when you're solving with goodness of fit method, because in goodness of fit method, you were given in terms of, it was frequencies, but in this one, you're seeing that we're going to be using a contingency table, right? And so it's going to be in rows and columns, and we're going to have variables, and then we're going to have the values for those variables. Now, the way we found degrees of freedom in goodness of fit method, if you remember, degrees of freedom usually is your k minus 1, right? Which means categories minus 1. Now, in independent method, your degrees of freedom is found by saying your row minus 1 and the total number of columns minus 1. And that's how we find that degrees of freedom. Another different thing is that in finding A sub O and A sub A, If you remember, when we're doing or learning goodness of fit method, our A sub O was always that the two are the same, right? So the observed and expected were the same. And then A sub A says they were different. But in the independence method, usually your A sub O will always say that the variables are what? Independent. And in A sub A, we'll say that what? Dependent. Right? And so that's the difference between one key difference between goodness of fit method and with independence method. All right. Now, one crucial thing to remember is that in this method, we are testing whether the occurrence of one variable affects the probability of the occurrence of the other variable. Right? I want to repeat that because that's very crucial. We're testing whether the occurrence of one variable, so variable A, affects the probability of the occurrence of the other variable, let's say variable B, right? And so that's a hallmark of this method. In finding our expected distribution, the method that we use to solve is a little bit different. So for expected frequency, right? For contingency table, right? These tables are arranged in forms of rows and columns, and we'll see one real quick that will make sense to us. So we'll find this expected frequency because you'll always be giving the observed, and you will have to find the expected frequency. To find that, the formula is actually the sum of your rows times the sum of your column divided by what? Your sample size. But we're going to use Excel to solve this, and it's pretty easy doing it. You won't have to go through doing it by hand, which takes a lot of time. All right. Now let's look at the steps to solving this question. Step one, we have to state our null and our alternate hypothesis. Step two, we need to know what our level of significance is. Step three, we need to find what our degrees of freedom is. And as you know, in this case, it's going to be a row minus 1 times your column minus 1. Step four, we'll always need to find our critical value. Step five, we'll have to find our p-value. And then in step six, we now need to make a decision, right? So we have to compare our p-value to our level of significance. And that allows us to make a decision, right, regarding A sub O. And then the last stage is we now have to interpret our results. All right, pretty straightforward with a few changes, right? And we're going to take it step by step to solve a question. And by the time we're done with this method, it's actually pretty easy to understand. All right, so let's look at a simple example. I'm going to click next slide, and we're going to look at a simple example. All right. So in this example, right, we're told that the contingency table shows that the results of a random sample of 2,200 adults. So this is the random sample of 2,200 adults. You can see total number of is 2,200. Now, so this is classified by their favorite way to eat ice cream, right? So you can see those male that eat with a cup is 600, female that eat with a cup is 410, right? That gives you 1,010. This number is called marginal frequency, right? Now, we're told to do a couple of things. they were told that they classify by their favorite way to eat ice cream and gender, right? So the question says, find the expected frequency for each cell in the contingency table. So we're asked to find the expected frequency. Remember, these values that we're giving here are observed, right? So we now need to find our expected frequency. Now we're told that at 1% level of significance, can we conclude that adults' favorite way to eat ice cream are related to gender? So we want to see if the favorite way to eat ice cream is related to what? Gender. Remember that in independence method, we're trying to see if there's a relationship between two given variables. In this case, we're looking at if there's a relationship between gender and the way they eat their ice cream, right? So that's what we're trying to do. And to do that, we're going to find our expected frequency, and we're going to use that to help us solve this question. All right. Okay. So step one is to state our null and our alternate hypothesis, right? So we're just going to go ahead and say that. Remember, like I said, in your null hypothesis will always be about being independent, and your alternate will be about being dependent. And remember, we're trying to see if ice cream eating is related to gender. That's dependence, right? So that would be H sub A. That helps you in how you write it, right? So you can say adults' favorite way to eat ice cream is, you can say, independent of gender, independent of gender. Or you can say are not related to gender, right? And then A sub A we're just going to make a slight change and say is dependent, right? So you can see the difference, right? A sub O would be about being independent, and A sub A would be about what? Being dependent. And that's what the key goal of the independence method is. Is it independent, or are these two variables dependent, right? All right. So that's our first step. Our second step is, as you know, level of significance, right? So we're doing a level of significance. And that would be 0.01. Go ahead and, all right. Our third step is asking us to basically find out degrees of freedom. So remember, degrees of freedom is just number of your rows minus 1 and number of columns minus 1. How you do this is you just want to make sure that you are doing it in the right way, so that we can calculate that. So for rows, we can say that's count, right? And this is for the number of rows, right? It's 1. And then for columns, we can do the same thing. It's 1. And we can see in this case, rows multiplied by columns is 1. So our degrees of freedom is 4. So basically, remember what we did is degrees of freedom is rows minus 1 and columns minus 1. Right? And so in this case, you can see the rows that we have is 2. So 2 minus 1. Columns, we have 1, 2, 3, 4, 5. That's 5 minus 1. So you have 1 times 4, you see 4. All right. So that's basically what we just did here. All right. So now we know that degrees of freedom is 4. And we know once we have this, right, we can go ahead and find our critical value, which it remains the same. So to find a critical value is still going to be a chi-square like we did. Inverse right tail. We choose our probability, which is 0.01. Our degrees of freedom is 4. So we now get that to be 13.27. Awesome. So now we found our critical value. Now, what we have to do now is, remember, we're told to find the expected frequencies. So we're going to have to create expected frequencies here. So we're going to make sure that we get these values. So I'm just going to copy this. I'm going to paste that. So the values remains the same, right? What is funny is that this is going to stay the same. Just going to copy this. Paste it here. See that has changed. Even the totals, you can copy and paste them if you want to, right? You can copy this. I'm just going to copy this ones. I'm going to copy just the totals for the bottom there. I'm going to paste them here. I'm not going to put the final totals because I want us to find it ourselves, but this is going to be very helpful for us. Remember the formula, right, here says that it needs to be the sum of rows times the sum of columns over what? The sample size, right? That's the formula to find, our expectant, right? Our expected frequency. So we're going to come here and say, okay, that'll be equal to, right? And this is where this becomes helpful. So we're going to have to copy this. I didn't want to do that, but we're just going to have to copy this. We're just going to paste it here. Because we're going to try to find the values inside here, right? Because those are the values that these are the values that are important anyways, right? So I can even go ahead and do this. These are the values that are important. All these values are only going to help us to find these values, right? And those are the expected frequencies, the values in here. And so it's the sum of, so do equal to sum of row, right? See where it says sum of row here? That's the sum of row, right? All right, multiply by the sum of columns, which is this one, divided by, right? Divided by this, right? So sum of row times sum of column divided by this, right? So I can put this in parentheses, so it's all nice and easy. Now, but remember, right? I can do this 1, 2, 3, 4, 5, 10, but that's a slow process. I want to drag it and make it easy for me. So I know that this number is not going to move. This is going to stay the same, right? And so I'm going to make this static by putting our constant by pressing F4 on my PC. For you, it will be Command T if you have a MacBook, right? I also know that this value is not going to move, right? This value is going to stay the same. So I'm going to make this 32 by pressing F4. Now, this one I'm going to keep because remember, if I'm dragging the sum of columns are going to move, right? 628 to 384 to 44 to 134. So those numbers are going to stay the same. So when I press enter, right, I get 550.8.909. But because I have that, right, and I can then click on here, I can drag. See, when I drag, you see it gives me the answer for all of this. This becomes my expected frequencies. Now, I can find the other one too by doing the same method, right? But this time I'll use 1000 instead of 1200 and do it. But it's going to give me the same result. It's just a waste of time. So I can do the second one easily by saying 1010 minus what? 550.909, right? I get 459.0.91. But if I did that method, I will still get the same answer. So let me just show you. So you can see it's 459.091, right? I'm just going to erase that. And I'm going to show you how that would work. If I did the sum of a row multiplied by the sum of the column and divide by 220 here, right? And that's, I'm going to go ahead and put my parentheses. When I press enter, you see I get the same. It doesn't change anything, right? I'll get the same results that I did when I subtracted. So you see it's the same. All I just need to do, I'll just need to do this one too, is just to put, make this static or constant, make this one also constant, press enter, and I can drag this and I get the same results, right? Same thing as subtracting from this. It gives you the same results. Now, these numbers here are now my expected frequencies. These numbers here were my observed frequencies. So now that I have these values, I can then find my p-value, right? I can then say my p-value will be equal to my chi-square test. And it now says actual range. I'll select actual range. And now it says expected range. I'll select expected range. And press enter. You see, it gives me my p-value, right? Let's turn this into real numbers and fix that. So you can see I have my p-value right here. And I can then compare it to my level of significance, is 0.1. And you can see that your p-value, my p-value is less, right? And once my p-value, if my p-value is less than the level of significance, right, we reject it all, right? I can also go ahead and find my test stat. Since I have this, right, I can go ahead and say my chi-square, and I can choose my p-value, and then select my levels, my degrees of freedom, and I press enter. I can see, right? I can draw this, and you can see how this works. You can see in this scenario, right? This is the critical value, which is, let's say here, right? My critical value here is 13.277. But look at my test stat, right? You can see the test stat here is 32, right? That tells me that it falls, my test stat falls here. So it falls in the what? The rejection region. Right? So even with my test stat, I can see I still rejected A sub O. So if you reject A sub O, which says that ice cream are independent of gender, that means you're saying that what? Ice cream, the adult's favorite way to eat ice cream is what? Dependent on what? Gender, right? So let's make a conclusion here. So we're going to make an interpretation. All right. We can conclude with 1% level of significance that, right, adults favorite way to eat ice cream are related to gender, right? So you can see that we're able to show that, right? because when we rejected this, it's of O, which says it's independent, and we went ahead to show that it's dependent, right, of gender. All right. I hope this helps you understand how to do chi-square, right? Quite easy. Based on this, right? This makes it easy for you to try it on your own, and I hope this helps you. For extra credit, you can try question 2, question 14, and question 15. Have a good day. Thank you.